Hi, I'm Lauren White. In this lesson, we'll talk together about how to rank nucleophile strength by analyzing steric hindrance. So first, let's remember what steric hindrance actually is. It's the concept that groups on molecules can get in each other's way, push each other around a little bit, repel each other, and cause that molecule to be a little bit unstable, higher energy. So more alkyl groups always means more steric hindrance. Now, for the purpose of nucleophiles, we want to minimize the steric hindrance. We do this because having groups on our carbons that introduce steric hindrance will make it harder for our nucleophilic atom to get into the nooks and crannies where our electrophile might be hanging out. So the general trend you want to know is that methyl carbons make the strongest nucleophiles, and tertiary carbons make not very good nucleophiles. So let's do some examples to dig into this a little bit more. For this question, we just need to rank these 4 nucleophiles in order of increasing nucleophilicity. So first, let's take a look at what we've got. We have these 4 molecules. We're told they are nucleophiles, and all of them have this OH group. Let's imagine that we have an electrophile that looks like this. Now remember, electrophiles are just electron deficient species, so they typically have a positive charge. Now notice, there are 3 other carbons around our positively charged carbon. So let's think about which of these nucleophiles would have the hardest time getting in there. Well, let's use an analogy again. Think about it like you're going to go swimming. Let's say you're trying to hand your younger sibling their pool toy. But they've got floaties on their arms, they're in a life jacket, they've got one of those big tubes around their waist. There's a lot of stuff between you and their hand to give them that toy. Now, imagine that you also have floaties on your arms, a life jacket, and a tube around your waist. There's going to be lots of squeaking of plastic as you try to get close enough to that kid to hand them a toy. Same idea here. Our electrophile is pretty bulked up with other carbons, which means a nucleophile that's also big and bulked up just isn't going to work. So the tertiary nucleophile here is going to be the worst nucleophile in this group. Still a nucleophile, but it's going to take a while. What if you were trying to hand that toy to your kid brother or sister and you just have on arm floaties and a life jacket? It'd be a little easier to hand that toy to them because, at least now you don't have that tube that's restricting how close you can get. This is the secondary nucleophile in here. In a secondary nucleophile, the carbon attached to our nucleophilic atom is attached to 2 other carbons. And so it's a little less restricted. So it's a little bit stronger. Now, to continue our analogy, let's say that you're actually a pretty good swimmer. You're not great, but you don't need any floats or anything like that. Now, compared to the other 2 situations, you can probably get that toy to your kid brother or kid sister before they start screaming. This is similar to our primary nucleophile. In our primary nucleophile, our carbon attached to our nucleophilic atom is only attached to 1 other carbon. So there's a lot less restriction in how easily it can get to the electrophile to react. Finally, let's say that instead of you giving your kid brother, kid sister the toy, you hand it to an Olympic swimmer. That Olympic swimmer is just going to fly through that water, toss the toy to the kid, then fly right back to their jet and go off and live the high life. This is our methyl nucleophile. It has just this 1 carbon. It's 180 degrees away from the OH group. So that OH group has something on its back end, but nothing actually crowding around it. So our methyl is the strongest nucleophile. So let's number these in order from weakest to strongest. Tertiary will be the weakest. Secondary will be a little better. Primary will be even a little better. And methyl will be the best. Now you should feel more comfortable ranking nucleophile strength by analyzing steric hindrance.